So we're finding volumes again. This is the last one for this, the washer method. The objective to find the volume of a solid using the washer method. So, first things first. Choose the correct formula to find the area of the annulus, i.e. a ring, below. Which one's right? B. Pi times big R squared, pi little r minus pi little r squared. The big circle minus the little circle. This is an important thing. This is what our formula comes from. Bless you. Okay. So consider the volume of a solid of revolution. Consider the region enclosed by the curves y equals x plus 4, that's the line, y equals x squared plus 2, that is the curved portion. So I'm taking that shaded area and I'm rotating it around the x-axis. So my axis of rotation is here. Okay. Can we use the disk method on this problem? No, because what the disk method requires is your axis of rotation is one of the lines on the boundaries of your area you're rotating. The thing that you're spinning around, the axis has to be, the boundary has to be one of them. It's a solid. This is a solid, but it's going to be a solid with a hollow center. So my axis of rotation is not one of my boundaries. I cannot use the disk. So what are we going to use instead? We're going to use the washer method, and I love this. What would it look like? Okay. Okay. Now we're going to find the volume of this funny shaped object. Okay. As in our disk method, set up a single rectangle in the region perpendicular to that line of rotation. So please, we're going to sketch this. Go ahead and sketch this in. You don't need in full detail like this, but it's the same basic idea. Okay. Please take note of the boundaries. Okay. So, yeah, we're spinning it around. This is our rectangle here. We're taking this as our rectangle and we're spinning it around so we have a matching rectangle underneath. Okay. Once again, our axis of rotation is not a boundary. So what do we have? If we take a look at it sideways, what do we have? We have a washer, which is a ring with depth. Okay, instead of a disk, which is a circle with depth, we have a washer, which is a ring with depth. So our formula changes. It changes accordingly. Okay. So do a quick sketch. Don't get carried away on the details. The things you need to know is you need to know the equations, x squared plus 2 and x plus 4. And you need to know the bounds. Okay. So what is the volume of this shape? And they're doing basically kind of, I know it's kind of hard to read, but it's basically giving the volume here of a ring. And so this there we go. Now it erased. We've got to rub a little harder to erase. So that's the volume of a ring. Pi big R squared, outer radius squared, times the height minus the inside, or I should say the big disk minus the little disk on the inside. Okay? Now, in order to do this, to write this as a formula, okay, what we need to do, and I love this one. This is a 3D of a surface. What you need to do is you need to come up with, let's see if they have it here. Here you go. This is the formula. So you take that ring, okay, If it was faster, we'd really watch it. Really isn't all that big a deal. So in order to find the volume of a washer, we've got 3 integrals now for volumes. One for slicing, one for a disc, and one for a washer. We took that volume of that washer, factored out pi, and the dx is the height factored out. So what do you have to come up with? You're going to come up with the outer radius, and you got to come up with the inner radius, and you got to come up with the bounds. Okay, you got to have the bounds, you got to have the upper bound, lower bound, big R, little r. Okay, label your diagram, sketch it out, label it out. That is absolutely, positively the most done. Let's see if it does this or not. Nope. Okay. So this is the one we were just talking about. Okay. We're going to take this and rotate it around. So we get a matching one underneath like that. Okay. This is the example we had. Bounded by y equals x plus 4, y equals x squared plus 2. So we're taking that region and that's what we're rotating around. So we need to find our bounds. How do I find our bounds? Yeah, set them equal to each other. Where do they cross? It's a system of equations. It's not a system of linear equations, so elimination by adding and subtracting ain't going to work. But all you have to do is say, hey, y equals x plus 4, y equals x squared plus 2, x plus 4 equals x squared plus 2, and solve for x. And if I recall, let's go back to here. Yeah, -1 and 2. I'm going to cheat because this is what we have, -1 and 2. So x equals -1 and 2. Those are our bounds. Okay. So our volume equals pi times the integral from -1 to 2. And then you got to figure out 2 things, big R and little r. Where's our axis of rotation? Our axis of rotation is the x-axis. That's what it's spinning around. I always like to emphasize that line. Little r, big R. Label it. Draw it. Yes, ma'am.
So the big R should go.
Always big R minus little r. Outer radius squared minus inner radius squared.
But should big R go to like the maximum point?
As far away from the x-axis as you can. As far as you can from the axis of rotation. And that's the thing you've got to know. You've got to line it up. Where's my axis of rotation? Because your axis of rotation might not be the x-axis or the y-axis. It might be another line altogether. Draw the diagram, and it really helps you see where that stuff is. But once again, draw a picture, makes a difference, yes.
So why wouldn't that big R be?
Well, because big R is the same, it differs depending upon where you're at. Because big R and little r is everywhere. Because there's the big radius, there's a little radius for that particular portion. Remember, it varies. How that distance varies depends upon where you're at. So the upper boundary of what I'm talking about, that's my big radius. The lower boundary, that's my little radius. And that varies as we go back and forth. So what is the function for my big radius? X plus 4. So big R equals x plus 4. Little r equals my parabola, x squared plus 2. So my formula is x plus 4 squared minus x squared plus 2 squared dx. Big R minus little r squared. This is another one, and I've talked about this with AP, and part of the reason I'm talking about how AP grades is because that's how I'm going to be grading. This would be like worth a couple of points. 1 point for each error. You don't square. That's an error. You have the R's swap. That's an error. Okay? And it's usually 2 minus 1 point for each error. That's 90% of what they do when they have these kinds of things. You get 1 point for the bounds and constant of integration, 2 points for this, and then 1 point for the answer. Remember, they have 9. They generally have 9. It is 9 points per question. They usually have 3 parts per question. So if they have 4 points for this, that means they have 5 points for the other 2 questions. So there might be other things. Now I have seen if the bounds are the same for every one, then you get 1 point for the bounds in A, B, or C, and then the other points depend upon the rest individually of the questions. They do that sometimes. So if A, B, and C, if the 3 questions all have the same bounds, they'll give 1 point for having the correct bounds in any one of those 3 problems. That's often what they'll do. I'm not going to work it out. I'll let you work it out and check with each other on that one. But that's the key to this, is doing what? Setting up the equation. That's what I'm really working at here, is setting up the integral. At this point, you can use the calculator to do it by hand. Either way, I don't care.
So it says find the volume. So
Yeah. What? No.
So
This will come out positive. This will be. Trust me. It will work out. Okay. Questions? Okay. Now this one will just kind of keep drawing as we go along. Find the volume of a solid revolution by rotating the area region bounded by the square root of x and y equals x squared about the y-axis. Notice how it rotated around. Okay. So once again, your first step. Draw a diagram. Y equals x squared, y equals the square root of x. Where are those 2 equations equal to each other? There's only 2 places where they're equal to each other. It's 0, and 1. Square root of 1 is 1, 1 squared is 1. And 0, 0. So our bounds, so this point here, obviously the origin, this point here is 1, 1. So our bounds are going to be 0 and 1 no matter what, well, essentially. Okay. Now the question is, what are we rotating it around? The y-axis. This is our rotation here. We're rotating it this way. So our problem is being done dy, not dx. So we need to change these into the appropriate ones. So this is x equals y squared, x equals the square root of y. It's almost the same thing. Okay. Then we're going to find our little r and our big R. Start at the axis of rotation. Go till you hit the first curve. That's your little radius. Once again, axis of rotation till you hit the second curve. That's your big radius. What is my big radius in terms of y? It's the square root of y. In terms of y, what is my little radius? Y squared. So my volume, pi. My lower bound again is 0. My upper bound is 1 from the square root of y quantity squared minus y squared squared dx. Sorry, dy, my bad. Thank you, dy, dy. I did say dx, I wrote dx, it's dy, my bad. So, and you think, and I'm look, you look at this right now, and what are you thinking? You're thinking, okay, wait a minute, that's going to be a negative volume, right? Because the square root of y is smaller than the square than y squared, right? Okay, well, if you square root, if you take the square root of y and square it, you get y. So it's y minus y to the fourth. What you're thinking, okay, that's bigger, right? Antiderivatives, 1/2 y, or 1/2 y squared minus 1/4 y to the fourth power, or 1/5 y to the fifth. Put in 1, you get 1/2 minus 1/5. You get 1/2 minus 1/5. It'll be positive, and then 0 minus 0 for the second part. So it is positive. It ends up being 0.2 pi. Right? Yeah. 1/2 is 5/10 minus 1/10 is 4/10, so you get 4/10, which is 2/5 pi. I think. 0.4. Sorry, 0.4. 0.3. I'm doing it wrong in my head probably, but that's okay.
So last one is rotated, not the
X-axis. This one's rotated around. Look at the picture. See the nice, pretty video?
And that's why you drew it on the y.
Yeah, because about the y-axis. It's a very important, very, very important part of it. You need to know the equations, but you need to know what you're spinning it around. Yes?
If this were on the test, they want it in terms of pi.
You can get both. Okay. If this is a non-calculator question, your answer is in terms of pi. If it is a calculator-based question, they will have both in terms of pi and a decimal without in terms of pi. Does that make sense? They'll have both answers. They'll have it, this one, what'd you guys get, 0.3 pi? Okay, so you get 0.3 pi. They'll take that and they'll have 3/5 pi. They'll have 3/10 pi, or they'll have 0.3 pi, and they'll take 0.3 times 3.14159, and they'll have that decimal out to 3 decimal places. They will have all of those answers if it's a calculator question. If it's not a calculator question, your pi will not. It will be in terms of pi because they do not expect you to multiply times 3.1415926. Okay, and you better not do 3.14 for pi, because if you do, I'm going to figure it out. I'm going to kick you in the butt. Because how many decimal places do you need to be minimum? Minimum of 3. Do 5. Minimum of 3. Do 5. 3.14 is not nearly adequate enough. Okay? Example 3. Find the volume of solid revolution generated about the region bound y equals square root of x, y equals x, rotated around the line x equals 2. So please take a moment. So your first step. Draw a diagram. So 0, 0, and this would be 1 for our bounds. That's not the big deal. Okay. Oh, actually, it is. So I have here. This is what I have, and this is y equals x. This is y equals the square root of x, right? And what's it rotated around? X equals 2. That's my axis of rotation. So, 2 things have to be considered. 1, what am I doing this dx or dy? This is dy, not dx. So instead of y equals the square root of x, it's x equals y squared. I have to change that. Now, little radius is not y. Because remember, this is xy, this is x equals y. So in terms of y, this equation is y. Okay. It is not. Y gives me this distance here. This is 2 minus y. 2 minus y. Because this, how far, what's this distance here? That distance there is what? It's 2. It's 2 units. So I go 2 units, and I go 2 units, and I take off y units. So it's 2 minus y. Big R, same thing. That's 2 units, and I come back to here. That's my big radius. My big radius is not y squared. My big radius is 2 minus y squared. That's the key. This is why you draw diagrams. Okay? So my volume would be pi times integral from 0 to 1 of 2 minus y squared squared minus 2 minus r squared squared dy. 2 minus y, sorry, 2 minus y. 2 minus y. 2 minus y. 2 minus y, not 2 minus r.
Do we have to find like are we supposed to solve this for like exactly?
Yes, you will. I'm not finishing that out because you can do it by hand or you can use your calculator. I don't care. My big thing here is setting it up. Solving it, it's up to you. Check with your friends and neighbors to see if you get the same answer they do. Okay. Yes.
On my calculator, I accidentally flipped it, so I did x squared minus 2 and then x minus 2 instead of the way you're supposed to do it with 2 minus x squared. I got the same answer.
Right.
So
Algebraically, that will work out because if you take if you take 2 minus x and square it, you get 4 minus 4x plus x squared. If you take x minus 2 and square it, you get x squared minus 4x plus 4. So you will get the same answer. And thus brings up a conundrum. Okay? This is one of those ones where, and I've seen it on AP where they go, if you have them reversed, they still will calculate the answers because it will still be algebraically the same. I don't recall whether they take points off or not for that. We may actually find out as we're going through stuff. But you will still get answer credit. They will still work out the answer. They may take off like 1 point for having it reversed, but because algebraically it's the same, they may not. Sometimes they don't because they're algebraically equivalent, so they don't care. Yeah, but 2 minus x squared and x minus 2 squared are exactly the same thing. Because what are you doing? You're taking the number, and if it's negative, you square it, you get the positive. If it's positive, you square it, you get the positive. You get the same algebraically, they're the same thing when you FOIL them out. Right? So what's the difference? But you should have it set up this way. Okay? Now, let's say we have the same situation. Same graph. Same equations. But our axis of rotation is x equals -2 instead of x equals +2. Slightly different. Because my little radius, or actually my big radius is this one here, right? And it's this distance from here to here, although it's -2 is where the line is, what's my distance? My distance is 2. My distance is 2 plus that. So my big radius is 2 plus y. Using the same equations I just did. Just changing where the axis of rotation is. And my little radius is this distance here, which is y squared, plus that distance, which is 2. This is why drawing a line is important, because there's a big difference between those two. Big difference between those two. My little r would be 2 plus y squared, or y squared plus 2. If I have something like I have two curves going like this, the difference between rotating it about this line and the rotating about that line is huge. It's huge. This one, you take this distance here and add it to whatever I have. Let's say that's -1. I add that to whatever my function is. This distance, let's say this is 3. I would have my distance here would be 3 minus whatever that function is. This would be plus whatever my function is to get from here to there. Very important difference between the two. This is why drawing a diagram, this is why this is my axis of rotation. What am I spinning around it? What is my distance from this lot, from my rotation to the first curve? What's it to get to the next curve? Okay, when you were doing a disk, it was the same thing. Even though your boundary was a particular line, if it's off, you may have to add or subtract to that function. Generally speaking, if your axis of rotation is on the opposite side of the x or y axis, what you're spinning it around is on the opposite side of the x-axis of what you're doing, or the opposite side of the y-axis of what you're doing, you're going to add that distance. If it's on the same side but beyond it, you're going to subtract. Generally speaking. Generally. Draw a friggin' picture. Label it. Find big R. Find little r. What are they? Draw the lines. Know that f of x, if this is f of x here, if this is a graph of my function f of x, that distance is f of x from the x-axis to the curve. If my axis of rotation is something else, I need to make an adjustment accordingly. This is why I cannot stress enough, drawing a picture makes all the difference in the world. And if I give you a picture, if AP gives you a picture, write on the freaking picture. They don't care. They don't actually see what you write when you draw the diagram. When you take the test, and I've seen the test booklets, they don't give them to me anymore. They used to give them to me after you guys got done with the test. Let me go ahead and pause this.